Actually, sorry, I have to stop and let me see if I can share the screen. Can everybody see my screen in presentation mode? Okay, I see yes. As I said, I can't see the chat, so please just shout out. Let me see now. Oh, I can have to stop that. Okay. Okay. So I assume you can see the screen, right? Yes, somebody.
Yes, it's okay.
Thank you. Okay, so this is the second part of the discussion we started last month on probabilistic graphical models. And as I said in the first part, I have to assume that we already covered the material in the first tutorial. So I will only focus here on inference and learning, just to give you a very, why I cannot. Yeah, overview of what we covered in a couple of sentences is that probabilistic graphical models is a way of representing high dimensional probability distributions, and probability distributions is the basis of all machine learning models, of most of them that they are based in statistics, and in such a way that the graph, we represent them with a graph as well as additional information like functions. And using the graph and the functions, we can represent a probability distribution, which is a mathematical formula with a construct that we can manipulate it with computer science or machine learning tools. For example, when we want to do inference, we can map the inference into a graph traversal, and we see that. In this, that was basically what we talk about different kinds of models, like undirected graphical models, directed graphical models, factor graphs, moral graphs, CRFs, conditional random fields, and so on and so forth. And we gave examples of these kinds of models, like how we can use them to model things in the real world. So what we did not cover in this part was once you have the model, which is usually what we call a parametric model, which means that you have a mathematical formula that has some parameters that you want to fit with the data. That means using the data that you have, your training data, your signals, you find values for these parameters so that the model fits the data or follows the data as close as possible. So that's the one thing. Yes, we said this is the parametric models, and we did not cover is how do we fit these models, like how do we find values for these parameters, and also once we have the parametric model or this probabilistic model, what can we do with this? How do we query? Okay, so in this and this is what we're going to cover in this tutorial. We'll start first of the second question, and then we'll see the first. The reason is first because it's an easier problem, and also some of the training models, training algorithms that we'll see, they actually use inference. And the reason also I wanted to include this tutorial, although it's a little bit more technical than the others, is because the algorithms and the techniques I'm going to use to talk are kind of a bread and butter for machine learning. Like it's not used on, I'm going to talk about them in the here in probabilistic graphical models, in context of probabilistic graphical models, but they are used anywhere that we need to do training or inference. Okay, So you'll hear about them a lot of times, for example, sampling or a maximum likelihood or expectation maximization. So I wanted to take this opportunity in the context of probabilistic graphical models to touch upon these techniques, which a person who wants to talk or use machine learning, even if they are not a machine learner or a data scientist, they should at least know of their existence and what they do, what is their purpose. Okay. So as we said, we'll start with inference. Excuse me, let me move this a little bit here. So inference. So as we said, given a probabilistic model, we are interested in using it to answer questions. For example, in the previous lecture, we talked about a probabilistic model that gives you the probability of a given email to be spam, given some input, and the input that we had there was the text of the email. Okay, so once we have this model, which was a probability distribution, and for us was going to be a function that we will be calling it, we will represent it as P. We don't care how it looks. We just know that it exists and we defined it. One thing we want to do is there are different kinds of inference, different kinds of questions that we can use. The first one is what we call marginal inference, which is to find the probability of a set of a subset of the variables when we marginalize everything else. For example, it could be, in our case, the marginal probability of the email being spam. So in this case, we said that how we describe this model is we have a label which we call the binary label spam, no spam, 0, 1. And then this is the y, the dependent variable, and we define our probability distribution P of y given the axis, and the axis here is the input, which is, as we said, the text. So the marginal inference, an example of marginal inference here would be to find the probability of x, or the probability of x equals 1. Okay. Another one is what we call posterior inference, which is the posterior probability given a set of when we know that some of when we give values for some of the variables. For example, in this case, it would be what's the probability of an email being spam when we know, for example, that x1 is 1 and x2 is 0. For example, that one word is papa and the other word is foreign. Okay, and the last one is what we call the maximum a posteriori, which is what is the most likely assignment of the variables, possibly conditioned on some evidence. So posterior inference and maximum a posteriori are connected in the sense that one can be mapped to the other. Okay. Any questions on this? And these are the three questions, these three queries that we will be using. Okay. Any questions here? No. Okay. So before continuing, I want to show the summary of the different methods that they exist, and some of them they can be used to answer all three of these questions. Some of them a subset of this, some of them are exact, and some of them are approximate, and we're going to see all of them. As I said, methods like MIP, which is mixed integer programming, sampling, maze, variational inference, or expectation maximization, which we'll see later, they're very well known and they're worth knowing. Okay. So the first one and the simplest and the basis of others is what we call variable elimination. Assume here, so we'll start with an example. Assume here that we have a Bayesian network, which is a chain, the one that is shown in the right part of the slides, where we have 4 variables, x1, x2, x3, and x4. And the graph tells us how the dependence between variables. So x4 depends on x3, directly depends on x3, x3 directly depends on x2, and x1 x2 directly depends on x1. In this case, as we had said in the previous slides, the previous tutorial, we can have in the graph, we know what is the how we can divide this probability distribution into different factors. So, and the probability distribution here is the joint probability distribution. That means the probability distribution of all the variables. So in this case, we would have the probability, the joint probability is the probability distribution of x1, x2, x3, and x4. And the graph tells us that the division on factors is P1. What it says here is that the probability, this is Px1 multiplied by Px2 given x1, multiplied by a probability Px3 given x2, multiplied by probability Px4 given x3. And the reason for this is because from the graph we know which variables are independent given other variables. For example, x2, x4 and x2 are independent given x3. Okay. And so having now the probability distribution, the joint probability distribution, we are interested in computing the marginal probability of Px4. Okay. So the naive way for this is the marginal probability is that we marginalize all the other variables. So it will be the probability distribution that we saw above by marginalizing x3, x2, and x4. Okay. Now, why this is naive way? Because if we write it that way, we basically need to find all the combinations of x3, x2, and x4. And an alternative way is that we will try to rewrite it in such a way that it pushes certain variables deeper into the product. And what we say when we say here pushes, we mean that we try to see whether we can marginalize one one variable independent of the other variables. And that actually it happened because, as we saw here, the factors that we have, they don't depend all of them all the variables. So we can, for the ones that we, for example, for one that does not depend on x1, we can take it out of the summation of x1 because it does not depend on x1, and that's basically the pushing of the variables deeper into the product. And that if we push it, we get a formula which looks more like the one in the last row, where we see that we can actually, by pushing the variables deeper, the marginalizations that we need to do, they become linear because, for example, we first need to marginalize on x1, which is linear on x1. Once we marginalize on x1, then the product that we'll get, the formula that we'll get does not depend on x1 because we already marginalized it. Then what we have here is that we marginalize that on x2. So we only need to marginalize them on x2, and then the x2, the result we'll get does not depend on x2, and so on and so forth. And that way we got from something that was to the cube of the variables, because we had 3 variables, to a linear form. And that's basically the variable elimination. Now, the advantages of this is that it can answer marginal inference queries for both direct and undirected networks. The disadvantage is that it is cumbersome how to find that, like how can we create an algorithm to find that? That's the question. And the other one is that the algorithm must be restarted from scratch from each variable. So for example, if we want now to marginalize on, here we marginalized on x, we wanted the marginal probability of x4. If we wanted to marginalize on x, to find the marginal probability of x3, we should restart the algorithm. Okay. Okay. Now, a step further is to see first how to automate that, and also to see it in a different way, so that we try to mitigate the problems that we just discussed. One way of looking at it is what we call message passing. So say, assume we want to compute, now I'll get a different variable, px3, in which case is get the marginalization of all the other variables x1, x2, and x4 of the joint probability distribution, which we saw in the previous slide. Okay, the first thing we do is that's where the moralized graph comes, is we get the directed graph, and we create the moralized graph. And just to remind you, what's a moralized graph is a graph, it is a way of converting a directed graphical model to a undirected graphical model. And how we do it is that first we see for every node whether it has for every two nodes, if they have a common child, we put, if there is no edge between the nodes, we add the nodes. In this case, we don't have that because we don't have childs of each child belongs only to one node, so we don't have to do that. And the other one is, once we do that, is we take out the edge directions. In each case, so to get the moralized graph here, we simply just take out the direction of the edges. Okay. So we go from the graph above to the graph below, which is just taking having undirected edges, and the nodes remain the same. And the other thing we'll do is that we'll route. This is a chain, but as we know, now we go in computer science and graph science. A chain can be represented by a rooted tree. And you can choose any of the nodes in the tree, and we'll choose as a root the node that we want to create the marginal probability on. So that in this case is going to be x3. So the chain that we had on the left can be converted easily, is equivalent to the chain that we see on the right. Okay. Now, once we have, we do that, it can be easily shown that the variable elimination that I did in the previous couple of slides can be represented with what we call the post-order traversal and of the graph. So and how is this going to be? So post-order, it means that we first visit the child for every node, its children, and then we visit the node. So in this case, we're going to take the first node that we'll visit is x1. So we'll see which one is the which formula has x1, f1 of x1. Exactly, I have it here. Yeah. Right. Sorry, post-order traversal, I'm wrong. Post-order traversal is we first visit, sorry. Let me get here, it's easier to see it. Yes, we first visit x1, which is going to be the, and for this one, we have the, as we said, excuse me, I got a little bit there. Yes, we want to see first what is we start with x1, and then the next one that we're going to visit is x2. So we want to see what is the formulas, the part of the formula that we have computed up to x2, and that's going to be the function that the part of the formula that has x1, which is f1 and x1, and the part of the formula that has x2 or x1 and x2, and that's going to be f2, x2, x1, x2. Okay, this comes from here. That's why we have in the left part f1 and then f2 of x2, x1. Okay, so that I'll call it another function. I'll call it m12 of x2. And why is x2? because at that point we already have marginalized the x1. So it's once we marginalize x1, it's going to be only a function of x2. Okay. So this is what this is the part of the summation that pertains to that part of the tree. Then we have the part of the summation that pertains to x3. In this case, is going to be whatever we had from x2 multiplied by the factor, any other factor that has this part, the nodes of this part of the tree plus x3. So it's going to be M1 and M1, 2, which we already computed, multiplied by F3, X3, X2, because these are the only other part of the formula that has the nodes of this part of the tree. And then the other one is, and we'll call that M1, 2, 3, and the other one is the part that comes from the other part of the tree, which is X4. And x3, that means every part of the formula that has x4 and x3, and that's going to be f4, x4, x3. And the final marginal probability is going to be m43 and m23. Okay, does it make sense? It basically, what I described here is a way of algorithmically pushing this product by using the tree in order to guide us in how to strategically add the summations, the individual summations, or the intermediate type summations. Any questions here? Sorry, I thought somebody had it.
Yes, one question. I thought that we had started from a chain going from x1 to x4. So
yes, so the same, yes, but that's what we said. First, we got the chain and we converted it to the moralized graph, which is the graph.
So what does that mean? So this means that we ignore the conditional dependencies.
No, so the moralized graph, as we said the previous time, is a graph that describes the way of the multi. How to say so the distribution has some factors like f1, f2, f3, and 4. Okay. And that's we found it based on the dependencies that we had in the graph, in the directed graph, right? We said x4 depends only on x3, x3 depends only on x2, and x2 depends only on x4. So the joint probability distribution of x1, x2, x3, and x4 can be represented by a multiplication of factors, f1 that depends only on x1, f2 that depends only of x2, x1, f3 that depends only of x3, x2, and f4 that depends only on x4, x3. Okay, so that is described by the directed graph. The moralized graph is a graph that represents the same factorization, but it's undirected. And the way we create this moralized graph is first, we get for every node, we check whether there exist different multiple parents of that node, and if there is no edge between that parent, those two parents, pairs of parents, we add an edge, and then we once we do this part, we can also ignore the direction of the edges, and that's how we go from the directed chain, which we have here, to an undirected chain. And because it's a chain, we don't need to do the first part. Because for every node has only one parent. So there is no parents to join. That's how we could go. Yeah. So that was again part of the previous discussion. So once we have that, then creating the tree was simple because, as we said, every chain can be described by a tree by choosing one of the nodes as the tree. And I chose the x3 because it was a specific choice because I wanted to marginalize to create the marginal probability on X3. So I had to marginalize everything else. So once I have that and I do the post-order traversal the way I described, and I find all these individual intermediate summations based on the post-order traversal, I actually created the pushing of the variables that I described in the variable elimination in an automatic fashion, in an algorithmic, let's call it, fashion, a fashion that somebody can easily program, like somebody can program this post-order traversal.
Okay, thanks.
So now, so that way we created. So what we did here is a mental exercise. We convert it into an algorithm, which is good because then we can create an algorithm, a software computer science algorithm that will be able to do this variable elimination. And we did it for X3. Now, say that we want now to compute the marginal probability of X2, the PX2. In a way, we're going to start over from the beginning. We'll create the moralized graph. It's the same as the previous step. We'll route it at X2, and we'll do the post-order traversal in order to find the intermediate summation. The intermediate summation. By the way, I will call these intermediate summations messages because that's how it is called in the literature, and that's where the message passing comes. Okay. And we'll do the same thing. Now, if somebody is astute, it's very hard because we go fast in the slides, we'll see that some of the messages, like for example, M12 or M43 are the same as in the previous step. So what it says here is that if we start over the algorithm, then we are going to repeat the computation. So if for example, we wanted to find all the marginal probabilities of all the variables, then we would be doing a redundant computation because we will be duplicating this computation. We'll be computing these messages, which, as you see, the messages, they are basically recursive constructs. They are defined based on other messages. So their computation can be quite complicated or time consuming. So duplicating the computation of messages that we already computed is redundant. Okay. And that's where the message passing comes, is that what if we compute all the messages once, and then once we have the messages, in order to find the marginal probabilities of some nodes, we can use the messages that we need in order to create the marginal probability distributions. Okay, and that's basically the message passing. This is, in the case of trees, it's called belief propagation. This algorithm, this message passing algorithm, we call it message passing because it is based on these messages, which is the intermediate computations of sums. And passing comes from, I'm using that, I'm using this message, this individual computation, in order to create another intermediate computation, another sum. So this message passing algorithm, in the case of trees, it is called the belief propagation. Belief propagation is computing all the messages at once for lower marginal probabilities. And once we do that, we show is that once we have all the messages, we can choose which ones we need based again on the tree and the rooted tree that we'll need in order to create the marginal probabilities of a set or all the nodes at the same time. Now, different names as
may I ask you, sorry.
Yes.
So the messages depend on the tree that you have chosen, right? So for different trees, you may have, for instance, if the root was X3, then you would have different messages by performing post order, right?
Yes, but you can see that the reason the messages are the same is that because parts of the tree are the same. So for example, let me show you.
Sure, but what are you gonna compute at the last step that you just described? Are you gonna compute the messages based on one form of the tree, or are you gonna compute something more than this? And then use whatever you need.
So are you asking me how I'm computing the marginal probabilities once I have the messages? The message,
no, I'm asking what is the set of messages that you are gonna, so here, for instance, you are gonna have 3 messages, right? But if the tree was different, you would also need something more or something different. So do you pre-compute all the potential messages that you may need for all potential trees that you may, come up with, or you just fix a tree, you pre-compute the messages, and then depending on what you need in subsequent steps, you are going to use some of them and compute others and add them in the set, and then etc.
Okay, first of all,
clear or not? I don't know.
I think it is. First of all, when we compute let me say something. No matter how how I want to say it, it doesn't matter what is the shape of the graph that we are going to use. We can fix the shape of the graph in one graph, and then based on that shape, we can find what are the marginal distributions that we need for every node based on the formula that I have in the middle of that slide. Okay. So the form of the graph, and these graphs, they're not completely different graphs. These are the same graph. We just define there's actually not it's the same graph. Before we were talking about, we were seeing different graphs because we were creating them as trees, and we were choosing one node as the root of the tree. Okay, but the graph is the same no matter whether you have it that way, because x2 is always connected with x3 and x1. x3 is always connected with x1, no matter how you draw it. So we don't change the graph. The graph is the same. So we can, for example, start with this graph, just the chain. The chain is this is the graph, and before what I showed before it was not different graphs. It's the same graph, being drawn different ways, and choosing one node as the root of the tree. But the graph was exactly the same. Does that make sense?
Okay.
Because you see, even here, like for example,
but,
like here,
because by choosing this tree here, the peaks, the message from x4 to x3 can be computed pretty easily. And
right.
If you choose, if you had a longer chain there and you choose another route, then that would be true for other nodes. And I don't understand very well, but I don't understand very well this notion of moralized graphs that you mentioned previously. And maybe this is the reason that I do not.
The moralized graph for you is going to be just an undirected graph, nothing else. Like for example, here, what I show here is the same graph. I just draw it different ways. The same graph, like x1 is connected with x2 only with x2, x2 is connected only with x3, and x3 is only connected with x4, right? Actually, I'm wrong. x3 is connected with x2 and x4, x2 connects x1, x2, in both ways I draw it, right? I'm just drawing it different, but the graph is the same. Okay. The reason I was doing it here that way is because I was computing. The first thing I was doing is I was trying to compute the marginal probability distribution of a particular node, x3, right? But what we said in belief propagation, we'll start by first computing the messages. And the messages are exactly the same. The messages that go through one node is exactly the same because it's exactly the same graph. So no matter how you draw it, the messages that they will go through that graph is the same because they only depend on neighbors of that. Yes.
Okay, I see. Okay, thank you.
Okay. Sorry, guys. Yeah, we're trying to actually say things. It is complicated because we are trying to say a lot of things in a small time. So anyway, so that was a belief propagations. I'm not going to go to the details. We already discussed it. We'll first compute all these messages starting from the what is called from the moralized graph, or if we don't start from a directly graphical model, we start, for example, for undirected graphical model directly from the undirected graphical model. And once we have the message passing, we can define, we can compute the marginal probability distribution for every node, given with a formula that's given at the end, which is basically it will be the part of the joint probability distribution that only depends on that node. In that case, say that I want to create the marginal probability distribution of x1, so it will be the part of the distribution that only depends on x1 if there exists, as well as multiplication of all the messages that come from the edges of that node. Okay, and these messages, as we described, they are recursively computed, and they're recursively defined. Okay. Now, one thing also is that another way of defining this algorithm or calling this algorithm is sum product, and that's where another construct, which is the factor graph that we saw in the previous time, comes in place. The factor graph was the undirected graph, which had all the nodes. It was an undirected bipartite graph. One form was the nodes, and the other ones was the parts of the probability distribution that the factors of the probability distribution, and one node connects to a factor, and a variable node connects to a factor node if the factor is dependent on that node. So, for example, if for example here I have an actually, let's go back here. F1 depends on X1. So I will have in the factor graph two nodes, X1 and one for X1 and one for F1, and there will be an edge between those two. So basically, the factor graph, we also add in the graph the factors of the probability distribution. And then this message passing has a very simple, the message passing algorithm has a very simple definition. Basically, in order to find what are the messages that go through a variable node, it is going to be the multiplication, the multiple of all the messages that come from the factor nodes that are adjacent to that node. And there is also a similar formula for the factor for the nodes that describe factor nodes. Okay, and so with a factor graph, we basically can very easily automate the message passing that we just described. And in the form of factors graph, they usually call it sum product algorithm. Okay. Now. So a variation, we're not going to get into the details. I just want to describe that of what is a junction tree algorithm, because it comes up a lot. Is a variation of the belief propagation that works on general graphs. Before, the ones that we saw before, it works on trees. It means that it is exact. That means that it finds the exact probability, the marginal probability distribution on trees. But there is a variation of this algorithm that works on general graphs, with a caveat that the graph can be described as what is called a junction tree. And what's a junction tree? Is you get your general graph, you partition the graph into clusters of variables. The clusters, the variables within the cluster can be highly coupled, and interactions among the clusters must form a tree structure. So in order to create the junction tree algorithm, one has to find a partition of the general graph into a tree in such a way that well, in this way that we partition the graph into classes of variables, we create, that means that we create groups of variables that we get into the same cluster, and then the structure of the clusters, excuse me, has to form a tree. Once we can do that, then we can perform belief propagation on the junction tree as opposed to in the individual nodes, and we find marginal probabilities of the clusters of the nodes. Okay, and that's basically the junction tree algorithm. The details are pretty hefty, so we're not going to go there. Now, on the other hand, excuse me, there is an approximate algorithm for general graphs, which is called Loopy belief propagation, which basically is this message passing on the general graph. This is approximate because we cannot prove that it is that it can converge. However, it performs well in practice. The thing that it does is that it discards the cycles, and once it discards the cycles, it can perform message passing or belief propagation on the resulting graph. And as I said, it's faster and it works surprisingly well in practice. Like for marginal inference, this is the go-to algorithm most of the times. Okay, because it is simple, and it performs quite well. Okay, and that concludes the computation of marginal probability distributions. Any questions here before we go to MIP? No. Okay, MIPs, as we said, we have the probability distribution, and we have some evidence. That means that we know the values of some of the variables in the probability distribution. And what we want to find is that we want to find values for the rest of the variables so that this probability distribution is maximized, and basically can be represented by the optimization problem that I have in the first line, which is argmax of the probability distribution. We get the logs for reasons of computational efficiency and performance, and is going to be we find the value of all the variables so that the value of the probability distribution or the log probability distribution is maximized. Okay, the details, I'm not going to go into the details, but we discussed it before. Usually there is a normalization constant, that's what we call here Z, so that the formula that we have, we can prove that it is a probability distribution that means it marginalizes to 1. And what it says here is that that does not depend on X, so we can ignore this marginalization normalization constant. Okay. Now, okay, so this is the formulation of the problem. So how we solve that problem? One way is using what is called the mixed integer programming. So that comes from the operational research community, where they have developed efficient algorithms, basically CPLEX, for linear constraint optimization on linear problems. And an extension of this is what we call the MIP, which is integer, which is mixed integer programming. So the usual linear problems, they assume that the variables that we have, they are continuous. Excuse me. And their algorithms, they have both, the variables are continuous, the optimization function is linear, and the constraints that any constraints that we're going to get is linear to the variables. The mixed integer assumes that is an extension that assumes that some of these variables can be integer values, usually notably binary variables, 0 or 1. Okay. So how we define how we map now the previous problem to mixed MIP problem. We introduce two indicator variables, and this is the variables that we will be the problem will be solving. So for every variable of the original problem, for every variable x1, xi, we introduce two indicator problems. One is mxi, and another is mxi is mixi, which is for every state of xi, for every value that the xi can get, we introduce another variable mxi. So if the xi has 3 states, 1, 2, 3, then we are going to introduce 3 new variables, m1, m2, and 3. Okay, and also for every edge, here I'm going to define the problem only on the pairwise graph. For simplicity, pairwise means that we have only edges between yes, we don't, sorry, I didn't say it correctly. The probability distribution is defined only between either nodes, single nodes, or pairs of nodes. So only between the node or edges of nodes. Okay, so for every edge node, they will introduce another indicator variable, which is for every edge in a pair of states xi, we introduce a variable mixi. So what does this mean? Is that if I have a variable with states values 1, 2, 3, that is adjacent to another variable with values 4, 5, 6, then we are going to create for every combination of 1, 2, 3, and 4, 5, 6 a variable miz. Okay, so that's going to be 3 by 3, 9 more variables. So you see that we create a lot of variables here. Then once we have these variables, excuse me, we rewrite the MIP objective using these variables. Okay, and this is the formula that we get. And the constraints that we'll have is that, as we said, the first groups of variables, they are binary, 0 or 1s. And the same as for the second groups of variables, which is between edges, is again 0 or 1. And the other constraint is that the first group of variables, mii, are going to sum up to 1. That means that every variable can only get one variable. Every variable can only get one value. So if we have a variable that we said that it takes with values 1, 2, 3, the constraint tells us that the solver can come up with a solution where only one of these variables is active, values 1 or 2 or 3. And the same thing for the edges. And also for the edges, we have another constraint, which is that marginalizing these variables, it gives us the value, marginalizing the edge variables gives us the value of the variable that defines on the value that is not marginalized. That means, say that I have a variable between an edge between variables with values 1, 2, 3, and 4, 5, 6, and we marginalize the edge constraint, the edge variables on the second variable 4, 5, 6, then the value that we'll get is going to be the value of the variable that defines the variable with 1, 2, 3. Okay. So that's basically it. And once we have that, we can solve it with off-the-shelf solvers like Rogue or Simplex. So basically, what this it's actually a very simple problem in terms of OR. What it says here is that I define a MIP problem that tells me for every variable which states are active. And states here is the values. Okay, and once we know if we know for example, for x1, the active variable is 3. For x2, the active value is 5, and so on and so forth. This, the set of active variables, this is the assignment that maximize this problem. Okay. That's how we map the MIP optimization problem that we described to MIP problem. And as I said, this is a simple problem, but it does create a large number of variables, a huge number of variables, which is basically the number of states for every variable multiplied by the combinations of states for every edge. Any question on the MIP? On the other hand, one thing here is that it is automated, it's fully automated. The things I described, they are fully automated, and there exist very powerful solvers like Loopy or Simplex. They can scale to millions. I think they've also done billions of variables. Okay, any question on the MIP before continuing? Okay, so the MIP, and that's where message passing comes again, can be solved also, turns out, with the message passing algorithm by replacing, in the message passing, we saw that we had sums, like every message is a sum of a function and possibly multiplied by another message. So if we replace the sum with maxes, then we can solve this MIP problem, and this algorithm is called max product algorithm. That's why I said the message passing is so powerful. It's an automated method that basically can cover a lot of cases. Now, it's usually slower than MIP approach because of the existence of the MIP solvers. However, they can easily be built into systems that implement message passing. And there also exists an effective approximate variation of this MIP algorithm, which is similar to the Loopy belief propagation that we described for the marginal probability. Okay. Now, another form of approximate inference comes for sampling. So this is actually comes from the domain of physics, statistics, physics, basically, because in physics they've done most of the work on how to sample from these high dimensional distributions. And so what it does is that once you have a multidimensional probability distribution, that means a probability distribution with a large number of variables, you can sample from that. And there exist different algorithms to sample these kinds of distributions: forward sampling, rejection sampling, the simplest one, importance sampling, and the most general ones is the family of Markov chain Monte Carlo, like Metropolis Hastings or Gibbs sampling. And the advantages of these algorithms is that they are generic. You can always sample. They're like using this. If you don't have anything, you can do rejection sampling. So you can always find an algorithm to sample from your probability distribution. The disadvantages is that it's difficult to tell whether you're close to an optimal solution. That means that the sampler has started sampling from the probability distribution, the actual probability distribution, and it's usually generally very slow to converge. That means that they actually take a long time to, you have to run them for a long time. And when we say long time, it's days to weeks, okay, usually for these distributions. So another one is what we call, any questions on the sampling? So one thing I want to say for the sampling is that some years ago we're creating probabilistic models from scratch for different kinds of problems was more popular than it is now, because now we usually use, if we can use a deep learning model, we use a deep learning model, and for that we already have a way of training it using the training algorithms for deep learning models that we've already discussed. Excuse me, sorry. Before we didn't have that, so sampling, once we would come up with a model, which is basically a statistical distribution, sampling was the first, or the, how to say, the general solution approach. If we could not find something else, always sample. Okay. Of course, then it was going to the time dimension.
Now, could you please say something about the the Markov chain Monte Carlo sampling? So what is the general idea behind this method? I'm
actually going to talk about a little bit about the Gibbs sampling, and then I'll talk about the Metropolis Hasting, which is the same thing. It's two different families. The reason I'm going to say Gibbs sampling is because it is more practical, and then but Metropolis Hasting is more general. So the Gibbs sampling is to say that you have a probability distribution of 10 variables. Okay. Your probability, you can write that joint probability distribution in terms of a conditional probability distributions. For example, one variable x1 given variable x2. So you can write this factorization of the probability distribution. And say that you have a way of sampling from this from these factors. Like, for example, I know how to sample from the conditional probability distribution of x1 given x2 and x3. For example, this is a Gaussian. We have an analytical solution to sampling. Then the Gibbs sampling, what we'll do is that you start with some variables. You sample some of the variables based on the samples of the conditional probability distributions. Then you will fix these variables, and you sample another set of variables based on their conditional probability distribution. Then you'll fix that, and you sample another one. So instead of sampling all of the variables at the same time, you sample in blocks. A block could be as small as one variable. Like, for example, one variable comes from a Bernoulli. Once you have sampled all of them, you repeat the process to get another set of values for all the variables. So basically, you sample by blocks. Okay. And
does this mean that you need to know which variables are dependent to one another?
So what you need to know is you need to have factorized the probability distribution in some factors, and then to know how to factor from how to sample from each factor.
Okay, so you have to have some prior knowledge there.
Yes,
some knowledge.
Right, but what it could be the case, though, why this is a better thing, that if you don't know anything, you can do rejection sampling. And the rejection sampling, what it does is that you have your probability distribution, you define a bounding box over that probability distribution, and you sample from the bounding box, which is easy because this is a uniform. The bounding box is a uniform probability distribution. Okay, and once you sample there, you check if this sample is within your probability distribution. If it is, you accept it, otherwise you reject it. So that's why this is called the rejection sample. So you always have a way to sample from a probability distribution. This is the rejection sample. It depends if you accept or reject a lot of these samples. Okay. Now, with Gibbs sampling, what it happens, what you can do is that say that I have a probability distribution of 3 variables. And one way I can do is rejection sampling, okay, on all these 3 variables. So I'm going to create a bounding box of 3 dimension, okay, in the 3 dimension X, Y, Z, and then I'm going to sample from there. But it might be the case that your probability distribution can be written as a Gaussian of 2 variables, of the 2 variables, and the Bernoulli of the 3rd variable. Then with Gibbs sampling, because you can use both the Gaussian and the Bernoulli to sample for your joint distribution, you don't have to revert to rejection anymore, and you'll reject nothing because for all your variables you have an analytical solution of sampling for these variables. Does that make sense?
Yeah. Okay. Thanks.
Now, Metropolis Hastings, it's kind of similar with rejection sampling, except that what you have there is that the rejection sampling, you always use the bounding box, which can be a bad or a good or a very bad solution, depending on how much gaps you have between the box and the what is called, and your actual distribution. In Metropolis Hastings, you defined, instead of using the box, this bounding box, you can define a different probability distribution that it's easier to solve. For example, you might define a Gaussian, which might fit better your probability distribution. Okay, and then if you define a Gaussian, you sample from the Gaussian, and then there is a criterion whether to accept this value or not. It's a little bit different from rejection sampling. That's the Metropolis Hastings.
Okay, thanks.
Okay, any other questions? Okay. So another form of approximate inference is what we call variational inference, and here is actually related to what we just discussed about Metropolis Hastings. I assume that we have a probability distribution, or a joint probability distribution P, and this is a very hard probability distribution to compute analytically, to compute the marginal or the MIP, but we are able to find a simpler solution, which is which is as similar to P as possible. So basically, with a variational inference, what we do is that if we can find this simpler probability distribution, then we substitute our original probability distribution with this simpler one, which we can do, we can analytically solve. And usually this simpler probability distribution is some form of a multi-dimensional normal. And what the variational inference does is that choose the class of tractable distributions, simpler distributions. As I said, usually it is a multi-dimensional normal, and then solve an optimization problem in order to choose from that class the particular one which is also similar to P as possible. Okay. The disadvantage of this is that almost never find a global optimal solution because we use a simpler distribution, except if it is very close, like extremely close to our original distribution, in which case it's going to also be intractable. It's on the other hand, it's very fast, and it can leverage any state-of-the-art computation techniques to produce the optimization, the MIP, stochastic gradient optimization, GPUs, and parallelization. Okay, because we define the class of tractable distribution. So usually this multi-dimensional normal, for which we have ways and algorithms to take advantage of these state-of-the-art computation techniques. Okay. So, and this concludes the part of the inference. Where we are. Any questions here before I continue to the training? Okay, so the learning. Okay, in a statistical, the graphical model is called learning. It's the same thing as training. As we said, it is identifying values of these parameters for our parametric models that we define. Okay. So the problem of learning is, given a data set, we would like to train a model that will make useful predictions on various tasks that we care about. And in the terms of graphical models, there are two forms of learning. One is parameter learning. As we described, we have a probability distribution that has some parameters. For example, my probability distribution is a normal with a mean and variance. And I'm training and fitting that, and I have some data, so I'm training the model in order to learn the values of these parameters, mean and variance. And also, there is another form of learning here is having a set of data, we want to estimate the structure of that graph. So far, what we've been doing is we've been given the graph, like part of our model construction was to define how this graph looks like. Okay, but an important problem or interesting problem is whether having some data we can estimate that graph. And this is called structural learning. Okay, so for the first one, the parameter learning, So again, we have to remember a little bit the previous talk. We discussed in the graphical models, we have models where all the variables are observed. That means we can observe them, we can see values of them. And also there we can define models where we have latent variables, and the latent variable here is variables that we can never observe. For example, crying, I am crying, you can see it, is an observable variable. Sadness or happiness, state of how somebody feels, is something that you cannot directly observe. So being sad could be a latent variable. Okay. Now, and this creates a complexity. So we'll start first with graphical models where we don't have latent variables. All the variables can be observed, we can measure them. Okay. Once for these variables, the solution to the parameter estimation, the training, the learning is usually through maximum likelihood. It comes from the field of statistics. So what we do is that we construct the likelihood, which is the probability of seeing the data. The data here is our training data, given the parameters, which is unknown for a given data set. So the data set here is the training data. And then we find the values of the parameters that maximize this likelihood, this probability of seeing the data given the parameters. Okay. So it's a typical maximization problem. So analytically solving this problem is usually expensive because of the normalization constant. Remember, in graphical models, we usually have a normalization constant in order to make sure that the probability distribution is the formula that we have is a valid probability distribution. And this normalization constant cannot, in the case of learning, be ignored because it is a parameter of theta of our parameters. So in this case, we might resort to approximate methods like gradient descent, what is used in deep learning models, or a technique that's used quite a lot and it's very effective is pseudo likelihood, where we compute the likelihood of a subset of variables, assuming the values of the rest of the variables are fixed. So this is similar to Gibbs sampling. In order to compute the likelihood here, we compute the likelihood of the subset of the variables. We find this, we keep that as part of the likelihood of those variables, and then we compute the part of the rest of the variables, assuming the first group of the variables is fixed. Okay, so it's kind of similar to that. Any questions on the learning for directing graphical models with no latent variables? No. It's really a typical optimization problem, parameter optimization problem. In the case of latent variables, maximum likelihood will not work. Will be actually very hard to apply, because in order to because my maximum likelihood assumes that all the variables are known, or the values of the variables are known. But this is impossible to happen when we have latent variables, because exactly we cannot measure, we cannot observe those variables. So what we will need to do in order to apply maximum likelihood is we'll need to marginalize them out. So that means that from a complicated distribution with the likelihood we already have, we make it even more complex by creating summations, marginalizations. So we create an even more complicated function to solve. And it's usually, well, most of the times, when you have latent variables, this creates, first of all, makes the formula of the likelihood intractable, and also it creates other things, like it makes it multimodal, so it's very hard to find a maximum multimodal models and so on and so forth. So what we usually do is we apply other techniques, and one of the techniques is what is called expectation maximization algorithm. The expectation maximization relies on two assumptions. Is that if the latent variables were fully observed, then we could optimize the local likelihood exactly as previously, right? like if they were observed, then we are in the first case. Now, knowing the weights, we can often efficiently compute the posterior of the latent variables given the variables that we know, the trained data, and the weights. The weights here is the parameters. Sorry. Okay. So how these two assumptions, how it is used, so the expectation maximization algorithm is that we given a data set, we start with some initial values for the parameters, and we repeat the same with the process until convergence, and it's the two-way process. In the first step, we compute the posterior of the probability, assuming that the posterior of the latent variables, assuming that we know the x and theta here is the parameters, and the x is the training data, the theta is the initial estimates of these parameters or the intermediate estimates of these parameters, and in the end step we compute the weights. Once we know these posterior distributions, then we compute weights solving a little bit of a different problem. Instead of solving the log, the max of the maximum likelihood, we compute the max of the mean the expected value of the likelihood, assuming that the latent variables come from the posterior distribution that we have computed in the first steps. Okay, and these steps are repeated until convergence. Now, I have to say here is that for the expectation maximization algorithm, if you see it, they usually write it a little bit different, but this is a way I have seen that I can actually use it in practice. They usually write in the first step to compute the expectation of the posterior probability given of the posterior probability latent variables given x and parameters, and then solving the argmax of this function, which is this expectation that we discussed. But the reason I say this is more intrusive is because the hardest part is to actually compute the posterior probability of the latent variable. So it makes sense for me to write that way. Okay. Any question on the expectation maximization algorithm? Okay. So the final, and this is the last slide, is I just want to touch a little bit upon on the structured learning, which is having some data, whether we can approximate, whether we can identify a graph. I'm not going to say the graph because, as we said in the previous time, there are multiple graphs that can define a set of dependencies, whether we can find a graph that approximates, that defines all the constraints that we see in the data, all the dependency constraints. So unfortunately, or fortunately, the research there or the work it's a very hard problem, so they're not real breakthroughs so far. So people, what they usually try to do, focusing on Bayesian networks, that mean directed models, is that they define a score which says how the Bayesian network fits the data, and then starting from an initial graph, and usually they start with a DAG, they don't go to general graphs. They search the space of different DAGs using some simple search like local search or greedy search, and try to find, incrementally find a different graph, a different DAG that gives a better score. Okay, and variations of this is how to search the graph, like with what order to expand the graph, or to make it smaller, or to add more branches, and how to solve the problem, how to incorporate the score on the search algorithm, on the search technique, again using the MIP approach that we described in the previous slides. And that's basically the state of the art of structured learning in graphical models. the actual state of the art, but it's not very recent. And I think until somebody comes with a breakthrough, it is a hard problem. And it's one of that they stay in limbo. Okay. So here, this concludes my talk. And I will, at this time, I will take any more questions that you might have before we make a very short break, and then we'll see the very short example of using these models. Any questions more here? I can say it again. Let's put it here. I don't see any questions. Okay, so then I'm going to stop this question, and I am going to. So for this, I'm actually having a couple of very little simple examples of defining a graphical model and doing some inference on that. Just give me a second to share my screen. So, share screen. Okay, so can you see my browser? I see. Okay, so the first one, so this will actually use information from both the previous and this tutorial, like defining these graphs. So first, I'm going to define the Bayesian network, a directly graphical model that describes whether a student or not is admitted based on some other variables, basically the student's marks, and the exam level, the IQ level, basically how good the student is, as well as a different variable that we have there. It's the score that it will get in aptitude scores. Okay, so assume that we have the variable, the graphical model, the Bayesian network that is described in this, where there are some edges, some arrows that probably you cannot see, so I'm going to say it. We define a variable that describes whether the student is admitted or not, say in a university. This variable depends on the marks of the students, the marks of their own specific exams. The marks of the students depends on both the difficulty of the exam level, and the IQ level is used here is a high or low, how the aptitude levels, I call it better. And also the IQ the level also defines the aptitude score. That means the scores that the student can get in standardized IQ testing exams. Okay. So having this graph, we can define the probability distribution of those the variables, the joint probability distributions, PAMIES, which is the probability A defines whether the student is admitted, defines the level of the marks, whether the student got good marks or not. I is the IQ level, is the difficulty of the exam, and S is the aptitude score of the student. So based on the graph, we know that the AA is, am I right? Yes, A depends on the marks. So we have this probability distribution can be written the conditional probability distribution of A given M. The marks depends only on the exam level and the IQ level. So multiplied by the probability distribution of A given I and E. I depends on nothing, is the top level node, PI, the same thing as PE. And the aptitude score also depends only on the probability of the IQ level. So the probability distribution of S, the aptitude score, given I. So that's how we can factorize the probability, the whole joint probability distribution of all the variables. Okay. So once we have that, there are some software that you can use in order to do simple inference. I use Pomegranate is good in the form that you can define a lot of discrete, several discrete distributions. And discrete distribution here is a multinomial. So the exam level is a probability distribution of whether it is exam level is two variables 0, 1, difficult or easy, probability distribution 0, 0, 7, and probability distribution 1 is 3. Same thing for IQ level. So we define that, and also the good thing is that you can also define what is called the conditional probability distribution, like the marks, which, as we saw, depend on the exam level and the IQ level, and we can define it here. So it's a good thing. Like it is kind of a reasonable software. Okay, and once we define the probability distributions of that, we have to define the actual graph, and this is defined here. That's right here. So every state is a variable, and you give the name of the variable as well as the probability distribution of that variable, or the conditional probability distribution. For example, in the case of marks, give the name marks and the probability distribution marks, which is a conditional probability distribution. Once we have that, we can visualize it. So it's a better visualization. We can see the arrows better here. And one thing we can do is inference. And the way it's doing inference here is Loopy belief propagation. That's their algorithm. And I'm doing marginal probabilities of given the exam level and the IQ level, the rest of the variables. That means the apt score, the marks, and the admission, whether the student is admitted. So the marginal probability distribution of exam and IQ is a specific value, the one that we give. And then the marginal probability of apt score is a discrete distribution with a specific value, values 0.6, 0.5, 0.6, and so on and so forth for the rest of the marginal distribution marks and admission. Any question here? Unfortunately, I could not find what is called a visualization of the actual algorithm. That's what I wanted, but unfortunately, there is no such thing. Okay. So, a simple example. Another simple example is, can you give me? Let's go here. Is that a similar example, but in this case, we're going to define, a Markov random field, which is another way of saying a non-directed model. So here we define a Markov random field of 4 variables, and there are 4 students: Alice, Debbie, Bob, and Charles, and we want to see describe the probability distribution of the students understand, whether the student has misunderstood, the teacher says something, whether the student misunderstood something or not. Okay, and using this, the connections, the relationships between the students, whether they're friends or not, we try to also define a variable, a network that defines these connections, these relationships. So in this case, we know that Alice and Bob are friends. So that we assume that if they're friends, they probably discuss, and they might actually have similar opinions on a particular problem. Bob and Charles study together. Bob and Charles. So because they study together, they have they have even larger affinity to agree on something. So they both have the similar probabilities of misunderstanding something or not. Debbie and Alice studied together, same thing. Alice and Charles, they can't stand each other. So we don't, we assume that because they don't talk, they probably, their opinion, one's opinion is dependent on the other. So we don't add the nets. And so how we create this graph, so on and so forth, how we create it. Now, once we have this graph, as we said, we define the edges based on our assumptions on how, whether there is a possibility that these variables are related, they have some relationship. So for example, Alice and Debbie, they studied together. So as we said, if they studied together, probably come up with the same understanding on the topics because they study and they discuss together, in which case that's why the affinity functions that we create, they give a large number on the cases where they agree and smaller number where they disagree. That is the top left matrix. Okay. So we give a hand trend because they agree, and when they don't agree. Now, one thing on the MRFs, as we said in the previous time, is that the functions that we define here, they don't need to be probability distributions. We just define some form of affinity, how our assumption, how we think they're related, whether we give large numbers when we think they're very related, small numbers whether we think that they are not related. Okay. And once we have this this MRF, we already defined the MRF. I used the Pygmy software again, another simple software that does simple factor graph analysis. So we'll define that as factor graphs. Again, the factor graph is the MRF, but we also add the functions. So the factors, that means the functions. So we define the discrete factors as we define them here. And then we add the edges that, the edges is between Alice and Bob, Bob Charles, Debbie, Alice. And we also add the factors. Now, one thing here is that we don't really need to define the edges between the factors and the variables, because from the keys, the software can identify that. So it does identify the local dependencies automatically. It finds that Alice is independent of Charles given Bob and Debbie. Alice is independent of Charles. It's exactly what the graph shows here. There is no edge, but there is an edge between D and B, exactly the dependency that we described, so on and so forth. And then we perform, having the MRF that we created, we do a variable elimination, as we described it, in order to find Debbie's affinity of misconception. That's the marginal probability distribution. And we find that Debbie has probability distribution, has an affinity of a large affinity to what is called to have a misconception in small, it's much smaller to not. And also using the MIP query, we perform MIP inference in order to find what's the Debbie's most probable state, and it's 0. That comes because we already know the marginal probability. It is it's actually very easy to identify that. We can also do map for what is called given some evidence. So for example, in this case, we say what is the probability distribution of Debbie to have a misconception given that Alice, and not the probability, what is the state of Debbie given that Alice has a misconception and Bob does not have, and that gives us the MIP based on that evidence. So the first MIP is without having any evidence, we don't know anything, so it only comes from the marginal distribution, and here we do MIP where we fix some of the variables on the values that are given. And that concludes my talk. At this time, I'll take any final questions if you have both on the slides or the examples. If not, let me stop recording.